Today we will discuss the strengthening mechanism of material. So, as you studied in the previous lecture, the main reason of plastic deformation is slip, and slip is taking place by a motion of dislocation. So, if we can impede or restrict the motion of dislocation, we can increase the strength of material. This is how you can change one of the property, that is strength, by doing microstructural modifications. So there are four different kind of mechanism. One is strain hardening, second grain size refinement, third solid solution alloying, and fourth precipitation hardening. Now we will discuss one by one. Now let us suppose you are having a material and you cold work that material. Each material is having some dislocation density within it. A normal material, annealed material, is generally having a dislocation density of 10 to the power 6 to 10 to the power 9. Now if you want to make it more stronger, you cold work the material. Say some kind of mechanical working, cold working of to a material. What happens during cold working? Now the number of dislocation increases and each dislocation is started impeding each other. So after cold working, the dislocation density generally increase to 10 to the power 12 to 10 to the power 14. It is like that in a room there are 50 students and they are moving here and there. If I fill that room by 200 students, then your movement will not be smooth. Means you cannot walk properly, you will hinder each other. The same thing is happening here. The dislocations, if the number of dislocations are more, they are hindering each other. Their strain field, stress field is hindering each other, and this way we can increase the strength of the material. So in this graph you can see this one. What is happening? There is a percent elongation, there is a amount of cold work, and on this axis we are measuring the tensile strength. As the amount of cold work is increasing, the strength of the material is increasing. Here strength is this, here strength is this, and here strength is this, but at the cost of ductility. Whenever you increase the strength of material, it is always, the ductility always decreases. So this is the formula. It is tau is the stress to move a dislocation in a matrix of dislocation density rho. Tau 0 stress to move a dislocation in the absence of any other dislocations. So you can say this shear stress is directly proportional to under root of dislocation density. Now next one is the grain size refinement. You know, two grains are having different orientation. In this grain, you see this is a one of dislocation. Whenever you are applying a shear force, this dislocation will move. Now this is a different grain, it is having a different orientation. So when this dislocation come at grain boundaries, to move further it has to change its orientation in this way, which is generally not possible. So all dislocation get hinders at the grain boundary and their motion hinders and their motion restricts. So we generally say the dislocations are piled up at the grain boundaries. So if you have a larger grain, two cases here, you are having two cases. One is this larger grain, another in the same one you refine the grain small grain. So if the grains are small, grain boundary will be more, and if dislocation will move, the hindrance will be more. So by refining the grain size, means by decreasing the grain size, you can increase the strength of the material. And this is given by the Hall-Petch equation, where yield strength is inversely proportional to 1 upon under root d. D is the grain diameter. So as you are decreasing the grain diameter, you are increasing the strength of the material. The third one is the solid solution alloying. If you add a foreign atom within that material, generally you are making alloy of copper and zinc. Zinc is going into the copper. So if the size of the host metal is larger than the the parent metal, then there will be a stress field. If size is large, then there is a compressive field. If size is small, there will be a tensile field. So whenever the dislocation will move, this stress field hinders the motion of dislocation. So this is showing here in this. We are adding, this is a copper, which is atomic radii is 1.28. This is the solid solution concentration on this side, 10%, 20%, 30, up to 40%, and here is the yield strength. We are increasing the percent of zinc in copper, we are increasing the percent of nickel, aluminum, silicon, different kind of material is mixed. We are making alloy of copper and these materials. So you say, if I plot light at this strength, silicon, this tin strength is this, and the nickel strength is this. So you can say a small percent of tin increase the same level of strength which nickel by nickel, which was nearly 25% of nickel. So you can see the mixing of metal to another metal is increasing the strength. So here another thing is that the difference between the parent atom and the host atom. So you can say copper 1.28 minus tin 1.51, it is difference, that is how much it is, and nickel 1.25. So only with copper and nickel difference is 0.03, and for this one it is nearly 23 angstrom, 0.23 angstrom it is point. So higher is the size difference, higher is the strength in the material. Or if you want to achieve the same level of strength, then you will have to increase the concentration of solute. Now third one is the precipitation hardening. Strength and hardness of metal alloy may be enhanced by formation of extremely small uniformly dispersed particle, which is called as a precipitates, in a second phase. So one is the matrix, submicroscopic distribution of precipitates. These precipitate also hinders the motion of dislocation. Let us suppose you are having this precipitate. The dislocation is moving here. So if the plane of dislocation is same as the plane of this precipitate, then it will be a cut through motion. Dislocation will pass through it. If not, then this will be surrounded like this. The dislocation is not able to move and they are hindering the motion of dislocation. This is how we can increase the strength of material.